This video shows how to use tree diagrams with conditional probabilities, and I think this is my favorite topic in the entire course. Conditional probability is a relatively complicated concept, but tree diagrams are visually pretty simple to understand, and they give a very nice way of making this concept of conditional probabilities rather simple and straightforward, at least in some instances. Let's start by thinking about dealing two cards from a deck of cards, and let's keep track as we deal whether or not the cards being dealt are hearts. If we do that with the tree diagram, the tree would look something like this. The first card will either be a heart or it will not be a heart. And if the first card is a heart, the second card will either be a heart or not a heart. And similarly, if the first card is not a heart. So this is the kind of tree diagram that was routine for us back in part 4 of the course. Now here's where the probabilities come into play. On each of the branches of the tree, we're going to put a probability. The branches are, of course, the lines that connect the things that are shown in the tree. When we deal the first card from the deck, there are 52 cards in the deck and 13 of them are hearts. So the chances of that first card being a heart are 13 out of 52. And similarly, the probability the first card is not a heart is 39 over 52, since 39 of the 52 cards are not hearts. So these two numbers that go on the two bottom branches of the tree are simply the probability of each of these things happening. Now once we get above that point in the tree, once we get above the first level, the probabilities entered are conditional probabilities. If the first card is a heart, then what do we have left in the deck? We have 51 cards, of which 12 of them are hearts. So the chances of the second card being a heart will be 12 over 51. And in the same way, the chances of the second card not being a heart, based on our knowledge that the first card is a heart, would be 39 over 51, since 39 of the 51 remaining cards are not hearts. On the other hand, when we move over to the right side of the tree, we're looking at the case where the first card is not a heart. And in that case, when we deal the second card, there are 51 cards left, of which 13 of them are hearts. So the chances of the second card being a heart will be 13 out of 51. Not being a heart would be 38 out of 51, since only 38 of the remaining cards are not hearts. Now, the nice thing that this does for us is it gives us an easy way of computing the probabilities for the outcomes. To compute the probability of an outcome, such as the one at the far left of the tree here, all we have to do is multiply the numbers that appear on the branches along the way. We look at the number that appears on this branch and the number that appears on this branch, multiply those two together because those are the two branches that lead from the bottom of the tree up to the outcome that we're looking at. And that product will give us the probability of that outcome. In this case, the probability of both cards being a heart is 13 over 52, the chances the first card is a heart, times 12 over 51, the chances the second card is a heart, if we know that the first card is a heart. We multiply these together and we get 1/17 as the probability that both cards are hearts. The reason this is mathematically valid is because of the definition of conditional probability. The probability of two things happening, if we think of a first thing A and a second thing B, the probability that both things happen is the probability that A happens times the conditional probability that B happens if we know that A happens. So we apply that in the case where we're looking at A being the event that the first card is a heart, B being the event that the second card is a heart. So B intersect A simply says both cards are hearts, and that probability is the probability of A, the first card is a heart, times the conditional probability of B given A, which is the probability the second card is a heart, based on the knowledge that the first card is a heart. So this method of multiplying the numbers on the branches to get the probability for the outcome is not magic. It's simply what the definition of conditional probability says we can do. Let's go on and fill in the probabilities of the other outcomes. The probability the first card is a heart and the second card not would be this probability times this probability. The probability the first card is a heart times the probability the second one is not a heart, based on our knowledge that the first one is. That product is 13 over 68. Similarly, we can do the remaining two cases. The probability the first card is not a heart and the second one is would be 39 over 52 times 13 over 51. And the probability of this far right outcome would be the number on the product of the two numbers on the branches that lead up to that outcome. 39 over 52 times 38 over 51. Now let's move to the kind of tennis match example we looked at in part 4. Michelle and Kim are playing a tennis match. The winner has to win 2 sets. In this scenario, Kim is the better player, and in fact, when they play a set, the probability is 2/3 that Kim will win the set. And then we have a variety of questions that are asked based on this scenario. The tree diagram is familiar to us from part 4. What's new now is that we're putting probabilities into the tree. In this case, the probabilities are relatively simple to put in because we know that any time they play a match, Kim's probability of winning is 2/3 and Michelle's 1/3. So every branch that shows Kim winning, we put in a 2/3 probability. Every match that shows Michelle winning, we put in a 1/3 probability. So to obtain the probability of any of the 6 outcomes shown in the tree, we just multiply up the branches to that outcome. So for example, for the outcome that I'm pointing to now, we would multiply 2/3 times 1/3 times 2/3 to get the probability that Kim wins the first match, Michelle the second, and Kim the third. If you do that for all 6 of the outcomes, you arrive at the probabilities that are shown here. The sample computation is for this one, 2/3 times 1/3 times 2/3, the numbers coming from these 3 locations, that product giving us 4/27, the probability of that particular outcome. Of course, you can check your arithmetic by adding up all the probabilities, the numbers in green here. They have to add up to 1 if you've done the problem correctly. The first question is, what's the probability that Michelle will win the match? Well, the 3 outcomes that show Michelle winning the match are the 3 shown in red, so we just need to add their probabilities. 2/27 plus 2/27 plus 1/9. Those numbers add up to 7 over 27, so that will be the probability that Michelle wins the match. The next question is, if Michelle wins the first set, what then is the probability she wins the match? Well, certainly winning the first set should increase her chances, right? So this conditional probability should be larger than the probability that we just computed. We're looking at the probability she wins the match based on the knowledge that she wins the first set. So we return to the definition of conditional probability to think about how to approach that. This conditional probability can be expressed as the probability of both things happen, that is, she wins the match and wins the first set, divided by the probability of the given information, which is that she wins the first set. And we can pull all of these probabilities right out of the tree diagram. Michelle winning the match and winning the first set happens in which cases? Here's a case where Michelle wins the match and wins the first set. Here's another case where Michelle wins the match and wins the first set. The only remaining case where Michelle wins the match shows her losing the first set to Kim. So the probabilities of these 2 outcomes, these are the only 2 outcomes that fit the numerator here. So the probability in the numerator is this probability plus this one. The denominator will be the probability of all the cases where Michelle wins the first set. And that would be the 3 on the right part of the tree, since in all of those 3 cases we show Michelle winning the first set. So when we do the arithmetic, calculate the numerator divided by the denominator, we get 5/9 as the probability that Michelle wins the match based on the information that she wins the first set. And of course that's a higher chance of her winning the match than the probability we calculated based on no information about who wins the first set. Now let's turn things around and see what's the probability Michelle wins the first set based on the information that she wins the match. So we're just reversing the situation now. What's the probability that she wins the first set if we know that she wins the match? Again, the definition of conditional probability says that conditional probability will be simply the probability that both things happen divided by the probability of the given information, which is in this case, that she wins the match. The numerator is the same as it was in the previous calculation because we're talking about the same 2 outcomes. These are the 2 cases where she wins the first set and wins the match. Now we're dividing by the probability of her winning the match, which would be the sum of the probabilities of these 3 cases, this one, and this one, since those are the cases where she wins the match. We add their probabilities and we get 2/27 plus 2/27 plus 1/9, which is 3/27, is the 7/27 shown here. Do the arithmetic and we get 5/7. So if we know that Michelle wins the match, then it's really quite likely that she had to win the first set in order to do that. And finally, what's the probability the match lasts 3 sets? Well, these are the outcomes that are shown in gray. These are the outcomes where it takes 3 sets in order for somebody to win the match. It's just a matter of adding up their probabilities. The probabilities of those 4 cases add up to 12/27, or 4/9. A little less than half as the chances that the match goes 3 sets. Aaron has t-shirts in 2 different drawers of his dresser. In the top drawer, he has 1 white and 1 blue t-shirt. In the bottom drawer, he has 2 whites and 2 red t-shirts. What he's going to do is reach for a drawer randomly and pull out t-shirts one at a time, not putting any back, until he has a white t-shirt. We're to draw a tree diagram for the process and calculate a couple of probabilities. The tree diagram will first consider which of the 2 drawers he selects from, and then what kind of t-shirt he pulls out of the drawer. The drawer will either be the top drawer or the bottom drawer. If he's fishing around in the top drawer, he'll either get a white t-shirt or a blue one, since that's all that's in the drawer. If he's in the bottom drawer, then he has to either get a white one or a red one. So our tree will look like the tree that's shown here. The reason we haven't circled either of these 2 outcomes is because the process isn't finished. Remember, he's going to be drawing t-shirts until he gets a white one, and in these 2 cases, if he gets a blue from the top drawer or a red from the bottom drawer, we're not finished with the process, so the tree will continue in those 2 cases. The probabilities I put in, 1/2 and 1/2 on the bottom level, that's based on the knowledge that he randomly picks one of the drawers to start with. Randomly is a key word meaning equal probability. If he's in the top drawer, since there's 1 white shirt and 1 blue one, that's a 50-50 chance whether he gets white or blue if he randomly pulls a shirt out of that drawer. In the bottom drawer, there are 2 whites and 2 reds, so that's 2 chances out of 4, or 1/2, that he gets a white one, and similarly for red. So let's go ahead and finish up the tree. If he's in the top drawer and his first shirt selected is blue, then the next one has to be white because there were only 2 shirts in the drawer to start with, so 1 white shirt is all that's left. So that probability is 1. We know for sure if his first shirt is blue, then the next one will be white. On the other hand, if he's in the bottom drawer and his first shirt is red, then what's left? He's still left with 2 whites and 1 red in that drawer, so the second shirt could either be white or red. 2/3 the probability that it's white, since 2 of the 3 remaining shirts are white. 1/3 the chances that it's red. And of course, if he gets a red shirt and then another red shirt, then he's got to go ahead and draw again, at which time he's guaranteed to get the white one because that's all that's left in the drawer, so that final probability will be 1. So we have 5 outcomes in our tree. We can compute the probability of each outcome just by multiplying up the branches. For example, this 1/6 is obtained by multiplying 1/2 times 2/4 times 2/3. Now, what's the probability he pulls out exactly 2 t-shirts from his drawers? We look in our tree and we see which cases those are. These 2 outcomes are cases where he gets a white shirt on his first draw, so he pulls out only 1 shirt. In these 2 cases, he pulls out 2 shirts. The white shirt is the second one he gets, and in this case, he pulled out 3 shirts. So these are the 2 cases we're interested in. We simply add their probabilities, and we get 5/12 as the probability that he altogether pulls 2 t-shirts out of his drawers. Now, what's the probability he's taking t-shirts out of the top drawer if you know he takes out exactly 2 t-shirts? Phrase it like this: probability top drawer, given that he takes out exactly 2 shirts. So the definition of conditional probability gives us that answer as this fraction. What are the cases where he's pulling from the top drawer and draws 2 shirts? That's this case right here, probability 1/4. The probability of drawing 2 shirts is the sum of these 2 probabilities, since these are the 2 cases where he draws 2 shirts. That probability we calculated to be 5/12. So this fraction is 1/4 divided by 5/12, which is 3/5. So the conditional probability we're looking for here is 3/5. Now we move to Tanya, who wants to pass a qualifying exam. She's allowed 3 attempts maximum, and each time she takes the exam, there's a 40% chance she will pass. We're going to draw a tree and answer some questions about the long-term probability of her passing. The tree will be as shown. She takes the exam the first time, she either passes or fails. If she passes, that's the end of it. If she fails the first time, she takes it again, in which case she'll either pass or fail. And if she fails the second time, she takes it again, at which time she'll either pass or fail. But if she fails that third time, that's the end of the road because she's allowed a maximum of 3 possible attempts. Each time she takes the exam, there's a 40% chance she'll pass, a 60% chance she'll fail, so that's where the probabilities in the tree come from. To calculate the probability of any of the 4 outcomes, we simply multiply up the branches as usual. 0.4 is this probability, 0.6 times 0.4, 0.24 is this probability, and so forth for the other 2 probabilities shown. Their calculation is as shown above. Question: what's the probability she'll pass the exam? Well, the 3 brown outcomes are the cases that she passes. We just add up their probabilities and we get 0.784 as the probability that she will eventually pass the exam. So even though she has only a 40% chance of passing on any given attempt, she has a fairly good probability of passing eventually simply because she's allowed multiple opportunities. Makes sense. Now, what if you know that she fails her first attempt? What then is the conditional probability she will eventually pass? Obviously, that's going to lower her chances, isn't it? Failing the first attempt is bad news, so that will lower the chances that she eventually passes. The probability that she passes, given that she fails her first attempt, is the probability she passes and fails her first attempt divided by the probability she fails her first attempt. Passing and failing her first attempt would consist of these two cases, so the sum of their probabilities is our numerator. Failing the first attempt, well, there would be all of these three cases, but it's going to be 0.60 because we can look down here in the tree and see the 0.6 probability that she fails her first attempt. So either get your denominator from looking here or from adding up these three probabilities, which are the probabilities of the three cases that start out with her failing her first attempt. In any case, the denominator here is 0.60. Do the arithmetic, 0.64. So her chance of passing drops from 0.78 something to start with to only 0.64 if you know that she has failed the first attempt.